Okay, so I have some some graphs here of functions that we talked about yesterday and a couple of days before. So remember that sheet that I gave you with all the parent functions on there? Okay, that might be helpful, but we'll go over this, okay? So take a look at this linear function I have here. It's the function f of x equals 3x plus 2. Do you see it? It's over here. Okay, what would be the domain of that function and the domain of any linear function? Just shout it out. What would it be?
All real numbers.
It would be all real numbers. Good. We're off to a good start. Yes, it would be all real numbers, and this is the funny looking R, the Gothic R that we're going to use to represent all real numbers. So every line that you see, the domain will always be all real numbers, okay? How about this quadratic function over here? All real numbers again. Yes, very good. Any quadratic will have a domain of all real numbers as well, all right? So far, so good. We're just getting warmed up to this idea of domain. Okay, this is a little bit different. The one on the left here is the square root function. So you should have some kind of an idea that that's what the graph looks like. So what is the domain of that function? You can just shout it out. 0 to infinity. Okay, great. So what we're going to do is we're going to write that as all real numbers x such that x is greater than or equal to 0. This is the new way that we're going to write these things, okay? All right, this is the cool kid way, yes. We are all cool kids, and this is the cool kid way. All right, this one over here, this is the reciprocal function. Looks like the Hurley graph. We spoke about this one. This one is a little bit different. How do you distinguish what this domain is going to be? There's something interesting about this one, and there you can come at it from an algebra point of view, or you can come at it from a graphical point of view. Lauren, what do you think?
All real numbers that are not 0.
Yes, this is all real numbers x such that x is not 0. So essentially, do you see that like when x is 0, there's this vertical line here, and in fact, this is the vertical line, x equals 0. Do you guys see that? Well, that implies something's going on there, all right? And if you look actually at the algebra, can you ever have 1 divided by 0? No. So from the algebra, we can't have 1 divided by 0. From the graph, it looks like our graph actually never hits this function at 0. So we're going to say the domain is all real numbers except for 0, okay? Different than the one that we had before, which is a square root function. So sometimes our domains are inequalities. Sometimes they are statements that don't include certain values. Okay. A little bit more advanced here now. What did I do? What's the difference between the graph and this graph? Huzaifa, my man, he's on top of it. Notice that I just moved this one over a little bit, and you should notice that it was indeed 3 units to the left because I have a plus 3 there. So that should be nothing new. So we would say all real numbers x such that x cannot be a negative 3. And this is the reason why it's a positive 3 goes to the left, because it has something to do with its domain value over here. And you'll notice that this indeed is the line x equals negative 3. It's a vertical line right there. Are we doing okay so far? Oh, thanks a lot. There we go. Good looking out. All right. Now, the most advanced one. Here we go. Take a look at this one. Ooh, this looks scary. All real numbers x such that x is not equal to negative 1 or, what'd you say? 3. Okay, so I love the fact that you just can look at the graph and tell me. What did you look for to see? Okay, guy?
Where it went up and where it went down.
Kind of like where the graph sort of split.
Yeah.
So like right here, you know there's something weird going on, and that's indeed the line x equals negative 1. I agree with that. And then same logic for this one over here, right?
Yeah.
X equals 3. I wonder if we could get those values from the algebra of that. How do I get a 1 and a 3 out of that? Anybody see it?
You have to do
It starts with an F, ends with an actor.
factor.
Yeah, we have to factor. Right, we have to factor. You guys did not catch that. Yeah, we need to factor that. So how could I factor x squared minus 2x minus 3? How could I do it?
X minus 1.
No, it's an x plus 1 and an x minus 3. And what do we want to know? We want to know when this is equal to 0. So we solve and use the zero product property. X would be negative 1. That's this one there. And x would be 3. And that's that one there. Do you guys see it? So that's going to be a technique that we're going to have. Whenever we have a rational function like this over here, we're going to factor the denominator and look for where it equals 0. So that should be nothing new, or you should make that connection there. But I love the fact that you can just look at the graph and say, I know exactly where the domain is because it can't be here or here, so it must be everything else. Okay? Okay, so I'm going to give you, we're going to spend the rest of the day talking about two or more functions. So if I give you any two generic functions, and I'll just call them f and g, so I have an f of x and a g of x, all right? And what we're going to do is we're going to talk about operations on functions. So operations, like what are the operations in mathematics? There's addition, subtraction, multiplication, division, right? There's only 4. Okay, so the first thing then, if I have these two functions, f of x and g of x, and if I want to actually add them together, like f of x plus g of x, I'm allowed to do that, and the notation that I would say would be f plus g of x. So this is the way that we write these things. So box 2 is all about kind of an abstract idea. Box 3 will give you an example of what we mean by this, okay? Same thing goes like this. If I want to take f of x and I want to subtract g of x, well, we can do shorthand writing and say it's the same thing as f minus g of x, all right? And this is an equality statement, so that means it works from going from the left side to the right and vice versa, right side to the left, okay? So what's the next one? Well, addition, subtraction, multiplication, right? F of x times g of x, well, that's just f times g of x, right? We are allowed to do that. This is the notation we can use. And then finally, if I want to take f of x and divide it by g of x, provided that, g of x is not equal to what, everybody? 0. Well, then it's just what you'd think it would be, f divided by g of x, all right? I realize that doesn't mean a whole lot in terms of, what I have here, but in the context of things, it makes a lot more sense. So let me give you an example in context. So let's give you the example, f of x is equal to, how about 3x plus 2, and I'll give you an orange one here, g of x is equal to, how about 5x minus 7, okay? What type of functions are those? Linear, quadratics, what are those things? Those are both linear, right? Okay, good. So let's say I want to do f of x plus g of x, right? Well, that's the same thing as f plus g of x. So what would that actually mean? Well, f of x is equal to what? What does it say up here? This is 3x plus 2. And then I'm going to add that to what? 5x minus 7, right? Because that's what that is. I'm just adding the two together, right? So when I'm all said and done, what do I have here? Well, 3x and 5x, that's 8x, right? And then 2 minus 7, how much is that? Negative 5. Okay, so here's the statement that we're making that students often don't make the connection to. So let's say I want this. Let's say I want f, what's f plus g of 2? What does that mean? What does f plus g of 2 actually mean? Yeah, okay, well, here's what it means, all right? It means take f of 2 and add that to g of 2, right? Okay, well, what is f of 2? Plug it in. It'd be 3 times 2 is 6, plus 2 is what? 8. Okay, good. And then we'll add that. What's g of 2? Well, that'd be 5 times 2 is 10, minus 7 is 3. Okay? So 10 plus 3 is how much? 11. Okay, so f plus g of 2 is this, but hey, guess what? I could have also just plugged a 2 right there. 16 minus 5 is also 11. So that's what we've actually done. Do you guys see that? That's the cool trick, though, okay? We could have also just plugged the 2 in for what f plus g of x actually is. And in this case, check it out. We would get 8 times 2 minus 5. Oh, look at that. We get 11. Oh, except I wrote 10. We get 11, and of course, it's the same thing as that right down there. So we'll do another example for you. Okay, and this is just f minus g of x. So we'll do it both ways, all right, just to show you get the same thing. So what is f of x? It is this. It is 3x plus 2. Minus, what is g of x? It is 5x minus 7. Very good, all right? So if I simplify this, what do I get? I get a negative 2x, all right? And then plus 9, right? You get that, right? So I went super fast here. Now, let's say I want f minus g of, we'll make it easier for ourselves, of 1. I could either just plug in a 1 for f of x and a 1 for g of x and subtract them, or just plug the 1 in right here for the actual combination, right? And I'd get what? 9 minus 2, I'd get 7 no matter what you do. Okay, sometimes we're going to take two separate functions, like I have this case, f and g, and we're going to actually either add them, subtract them, multiply them, do something to them, and then find the domain of that new thing. Okay? So, for example here, I want to do this. I want to take f plus g of x, and I want to find the domain of that. So I want to get this answer and then find the domain. Well, I know that this is just f of x plus g of x. That part's easy, right? And what's the value of f of x on the screen? What would it be? That's the square root of an x plus 3. Good. G of x, what's that? That's the square root of an x minus 2. Okay, good. So now this thing right here, this represents f plus g of x. Now, how do I find the domain for my new thing, my new f plus g of x? How do I do that? We could graph it, okay? So one trick you can do is look at their individual domains. So what would the individual domain for that be? Can you tell me? I'll start you off. It'd be all real x such that x needs to be greater than or equal to something. What would it be? It would be negative 3. How come? Tell me why. Yeah, because that's the shark fin moved 3 inches to the left, so everything's bigger than that, right? Okay, what about this one over here? This would be all real numbers x such that what? Greater than or equal to 2, alright? So now that you have both individual domains, look what happens if we graph them on the number line, okay? Here's 0, here's 2, here's negative 3. So we want everything that's greater than or equal to negative 3, so that's all this stuff, and then everything that's greater than or equal to 2. So you guys tell me, where do they overlap? They overlap when that's from 2 and on. See that? So therefore, it must be the case that the domain for my new function, this guy's domain, must be all real numbers x such that x is greater than or equal to 2. Does that make sense? Okay, so this is kind of similar, but practice with it, alright? Everyone gets messed up with these square roots. So I want you to add the two together, and then I want you to find the domain of the new function f plus g of x. There's the answer to the should have got that, alright? Function composition, here we go. This is not function addition, subtraction, multiplication, division. This is actually putting a function inside of another one. So as an example, here's the notation. You're going to see this. It's going to look like this. Okay. Now, hold on a second. That does not say fog of x. So please don't say fog of x. Nor does that say f times g of x. What this actually means? Yes, f of g of x. Okay? Now you have to realize which function is inside of the other one. Yes, g is inside of f. So that means that if we have two different functions, we take the input and we put it into g, and then out pops g of x, and then we take g of x and put it into f, and out pops f of g of x, okay? So it's a composition of functions. Kind of strange. When you see this, the way that you read this, like everyone just did, just to make sure I have it, is f of g of x. This is the modern way that we say this, the modern notation, okay? Don't say fog x. And don't say goff of x either. And when you see this, okay, goff x, that's not what that means. And by the way, are those two necessarily the same thing? No. Very good. We're going to learn that today. Okay, so let's do an example together, all right? I've given you two functions. I've given you 2x, and I've given you 2x squared minus 3. Okay? All right. So let's do this. Let's do one. Let's find f of g of x, and number 2, let's find g of f of x. Okay, well, let's see here. The first one, what does this mean? Well, this means to do f of g of x, right? So that means that we're going to do f of g of... Oh, I wanted to do an actual example here. Oh well, let's do that. Okay. F of g of x. So we're actually going to do f of, what is g of x? It's 2x squared minus 3. Do you guys see that? Okay, what do I do with the 2x squared minus 3? I plug it in for f. You guys totally get this, right? So I take this information and I plug it right there for the x function. So we get this. We get 2 times 2x squared minus 3, which ends up being 4x squared minus 6. Is that what you guys got? Okay, good. Now let's do g of f of x. I'll go orange here for you. This means g of f of x. That means g of, well, 2x, right? What does that mean? That means take 2x and put it right there for your g function. So we're going to have 2 times 2x squared and then a minus 3. So that's going to be what? So yeah, 4x squared times the 2. So that's going to give me 8x squared and then minus 3. Okay, please take notice, you guys. Those are extremely different. So it is not the case that every time f of g of x is the same as g of f of x. Okay? I'm going to go over to the left a little bit, and I'm going to ask that you do this really quickly. Please give me f of g of 1. Ready, set, go. Okay, the last idea is to figure out domains of composite functions. So what that means is, well, when I put a function inside of another function, what happens to its domain? Sometimes nothing, sometimes something very interesting, and sometimes it's hard to figure those out. So here's what we're going to do. I want us to figure out what f of g of x. I want the domain for this. What is the domain for f of g of x? This is our burning question here. All right? We're going to try and figure that out. All right, well, first of all, our answer is going to be this, in the form of all real numbers x such that, and then we have to figure out what this is. Okay, so we'll just keep that going in the bottom right-hand corner. All right, let's do this. First, let's find the individual domains for each of these two functions that I have. So we'll go blue. So what is the individual domain for f of x? All real numbers x such that x cannot be what? X is not allowed to be 1 in this case. So here's my domain for f. You guys agree with that? And the reason it can't be 1 is because I get a 0 on the bottom, and then I divide by 0, and that'd be bad. Okay? What about this one over here? All real numbers x such that x cannot be what? X can't be 0. Why can't x be 0 in this one? You can't balance on a ball. There you go. Can't divide by 0. It's undefined. Okay, so far I have these two individual ones, right? Now I'm asking for the composite function f of g of x. So which function is inside of which? Write it down. What is it? Yeah, so this is f of g of x, right? That's what this means. Do you guys agree with that? Okay, now, so if g of x is first, well, what's the very first thing I cannot allow in my composite function given the fact that g is first? 0. So I know right away that the composite function x, there we go, all numbers such that x is not equal to 0 is one of them. I cannot allow that, right? Because if I put it in a 0 for g, boom, I already get an error, right? Okay, now, there's a number that I call a number in disguise. And the number in disguise is this. What's the one thing that f is not allowed to be? Okay, it's right here. We know this. F of x is not allowed to, we can't evaluate a 1 for that, right? So keeping that moment in mind here, we have to ask ourselves, well, is there a number that when I plug it into g, since that one's first, that g turns it into a 1? Oh, good. See, you guys see it, right? So what we need to prevent is this. So g of x is never allowed to produce a 1. Do you guys see that? Ah, strange. So then you say, okay, well, that means that 3 over x is never allowed to be a 1. That implies that x is never allowed to be what? 3. Very good. So the composite domain is this. All right? All real numbers such that x is not 0 or 3. The interesting thing is that what number is not part of the domain of the composite? 1. Isn't that cool? Because 1 becomes a 3 when you plug it into the g function first. All right? Okay, same idea here. We're going to find the domain for f of g of x. Well, we know it's going to be all real numbers x such that x blah blah blah, right? We're not sure what it is yet. Well, let's go back to the original ones, right? What's the domain for f here? All real x such that x is not what? Not equal to -2, right? -2. What about this one over here? All real x such that x is not equal to 0. Very good. Okay. So since g is inside of x, we know right away x is not allowed to be a 0. You guys get that part? Okay, now what are we preventing? G of x is never allowed to produce what? A -2. When will that happen? Well, if I set g of x 1 over x equal to the thing that it's not allowed to be, it'll tell me. So x, I'm getting, if I solve this little equation, I get what? -1/2. So therefore, if x was a -1/2 and I plugged it into g, it would become what number? It would become -2, and then that's not allowed for f. So therefore, the composite domain, -1/2. So the last thing is for you guys to try to give me the domain of the composite for g of f of x using the same functions as above, g and f right there.